So the last section of Chapter 1 covers absolute value equations and inequalities. So friendly reminder that our absolute value is a measure of distance. What we're measuring is our distance from the origin, which is 0 on the number line. And it's always going to have a positive value. There are 3 types of absolute value equations and inequalities. So the first one is if I have the absolute value of x plus b is equal to k. That means the absolute value of x, it's the same solution set as ax plus b equals k, or ax plus b equals negative k. So for example, if I have the solution set that absolute value of x equals 4, that's going to be the same as x equals 4 or x equals negative 4, or meaning union and meaning intersection. If I have the absolute value of x is greater than 4, this is going to have the solution set x is less than negative 4 or x is greater than 4. So what does this mean? This means I have greater than, and we're going to use or. So let's use that. We're going to remember the term GOR. Greater than or. Next, I have the absolute value of x plus 5 is less than k. So that means I've got x is greater than negative 4 or x is less than negative 4. Greater than uses and. Less than uses and. So we're going to, you remember the word land. So now we're going to remember the term GOR land. Greater than or less than and. Greater than or less than and. GOR land. This is kind of a mnemonic, but not really. Just a way for me to help us keep our equations straight. So if I have 2x plus 1 equals 7, that's going to mean 2x plus 1 equals 7, or 2x plus 1 equals negative 7. I'm going to solve both of these, and my solution will be the union of the solution sets. So I have to subtract 1 from both sides. 2x equals 6, so x equals 3. For here, I'm going to subtract 1 from both sides. 2x equals negative 8, so x equals negative 4. So my solution is 3 or negative 4. Next, I have 2x plus 1 is greater than 7. Greater than, we're going to use or. So I've got 2x plus 1 is less than negative 7, or 2x plus 1 is greater than 7. One or the other. I'm going to subtract 1 from both sides. 2x plus 1 is less than oh, I already did that. So 2x is less than negative 8. So I get x is less than negative 4. Next, I subtract 1 from both sides. I have 2x is greater than 6. So I have x is greater than 3. So I have x is less than negative 4, or x is greater than 3. I'm going to go ahead and graph this on a number line, okay, so we can see the solution. Oh gosh, I've run out of space. Let's go ahead and graph this really gingerly in blue. So here I have negative 4, 3, negative 2, negative 1, 0, 1, 2, 3. Not the best number line in the world, but it works. So I have x is less than negative 4. We're going to plot that in green. I have negative 4. It's not included in my solution set. X is less than negative 4, so I'm going to shade to the left. Now I have x is greater than 3. We're going to mark that in red. Here's 3. 3 is not included in my solution set, and it goes to the right. How do I take the union of these two sets? Well, we're going to have to use the union symbol. I have negative infinity to negative 4, union 3 to positive infinity. That's going to be our solution set because we're using or, which means union. Next, I have 2x plus 1 is less than 7. So for greater than, we use and. I'm going to rewrite this. I've got 2x plus 1 is greater than negative 7, and 2x plus 1 is less than 7. I'm going to solve these. I get that x is greater than negative 4, and I get that x is less than 3. I'm going to go ahead and draw a beautiful number line again so we can compare our solution sets. In green, I'm going to plot x is greater than negative 4. Negative 4 is not included. Everything to the right is. And then in red, I'm going to plot x is less than 3. 3 is not included, but everything to the left is. And it means I'm looking for the I'm looking for the intersection. Okay? And means I'm looking for the intersection. So what I'm going to do is I'm going to go ahead and take the intersection of these two. That's where both red and green are touching, which is from negative 4 to 3. And that is my solution set. Let's keep going with a few more section 1.7 examples. If I have the absolute value of x plus 3 plus 5 equals 10, I'm going to go ahead and subtract 5 from both sides in order to isolate the absolute value. So I have the absolute value of x plus 3 equals 7. Using our 3 types of absolute value inequalities, I have that x plus 3 equals 7 or x plus 3 equals negative 7, right? Because our absolute value is going to be either positive 7 or negative 7. Absolute value is a measure of distance. This means x equals 4 or x equals negative 10. This is my solution set, negative 10 or 4. Now I've got a greater than symbol. Greater than uses or meaning union. So I'm going to go ahead and subtract 5 from both sides. I have x plus 3. The absolute value of that is greater than 7. So that means that x plus 3 is less than negative 7, or x plus 3 is greater than negative 7. I solve both sides. Is greater than positive 7. I solve for both sides. I get x is less than negative 10, and x is greater than 4. Let's go ahead and plot this on a number line so we can see what's up. Here's negative 10, negative 5, 0, 5, 10. I'm going to plot x is less than negative 10 with endpoints not included, and it's everything to the left. I'm also going to plot x is greater than 4. Here's 4. 4 is not included in my endpoint and includes everything to the right. If I want to write this in interval notation, I'm going to go from negative infinity to negative 10. And I'm unioning that, right? Or greater, we use the union. I'm unioning that with 4 all the way to positive infinity. And that's how we write this solution set in interval notation. Now when it comes to working with two absolute values, I'm going to go ahead and write x plus 6 equals 2x minus 3, or x plus 6 equals the negative of 2x minus 3. I'm going to solve this. I subtract x from both sides. I add 3 to both sides. I get 9 equals x. I distribute that negative 2x plus 3. I add 2x to both sides. I subtract 6. I have 3x equals negative 3, so that means x equals negative 1. My solution set for this is going to be negative 1, comma, 9. The last thing we're going to talk about in this chapter is special cases of absolute value. So, friendly reminder that the absolute value of an equation can never be negative. So if I say the absolute value of an equation equals a negative number, there's no solution to that, right? So our solution set would be the null set. However, if I say the absolute value is greater than or equal to a negative number, this is always going to be true, right? Because absolute value can never have a negative value. So our solution set is going to be for all real numbers, that's from negative infinity to positive infinity. Last but not least, is that if an absolute value expression equals 0, that can only be true when the expression equals 0. So let's look at a couple of these examples. So here I have 5x minus 3 equals negative 4. Well, absolute value can never be negative. So the solution here is there's no solutions, it's the null set. Now I have the absolute value of x is greater than or equal to negative 8. This is always going to be true, right? Regardless of whether x was positive or negative. So my solution set goes from negative infinity to positive infinity. Next, let's go ahead and simplify this. If I add 3 to both sides, that means x plus 6 is less than negative 2. Sorry, the absolute value of 6 is less than negative 2. This is never going to happen, right? This absolute value could never be less than negative 2, which would be all these negative numbers. So I have no solutions. If I subtract 4 from both sides, I've got x minus 7 is less than or equal to 0. And again, this can never be the case unless this was 0. So my only solution would be 7.